So make sure you bring this to the test on our next test. And basically this is just talking about how reactants decay. Okay? So in this whole chapter that we're talking about rates, okay, we're talking about how fast a reaction will proceed, how fast reactants will go to products. Okay, in this case, how fast? How do we measure how fast? We measure how fast based upon how much this decreases. Okay, and the way this reactant decreases, whether it's zero order or first order or second order, how fast, or the order of this decay, that's another word here, decay. Okay, how fast the decay of reactants goes to make products, how fast this happens will give us information about the rate. Okay, so how much we have, some rate constant K for each reactant. So if there's two reactants, you'll have two concentrations, but each reactant will decay in its own specific way. Okay, and this is why we want you to bring this to the exam. It can decay either with zero order, first order, or second order. So if it's zero order, you're going to use this equations. Okay, and this is the equation for half-life. If this reactant is going to decay with first order, you're going to use this equation, and this is the equation for its half-life. And if this reactant is going to decay with second order, you're going to use this equation, and this is its equation for the half-life. So this rate constant, lowercase k, is going to have different units. Right? So where we left off on Monday, we did some practice problems. Let's see if we can do some more problems here. I'm starting on page 11. Okay, so one more thing. Okay, bring to exam if I haven't told you this already. Okay, bring this sheet to the test. Alright, so a little bit about first order reactions. This is the equation that tells us about first order. Okay, one thing that's interesting about first order, I don't know if you want to get deep into this, but the half-life, okay, this is T1 half called the half-life, for first order is 0.693 over K. Okay, which is the same thing as natural log of 2 over K. Okay, natural log of 2 is 0.693. 0.693 on your calculator is the same thing as natural log of 2. Natural log of 2 in your calculator is 0.693. But what you see is missing here is that it doesn't matter how much you start off with. Okay, so here, your half-life depends on how much quantity you start off with. Your half-life here depends on how much quantity you start off with. For first order decay, very, very weird, very, very peculiar. Your half-life doesn't matter if you start out with 1,000,000 grams or 1 microgram. The half-life, whether you start off with 1,000,000 or 1 or a lot or a little, it's always going to be natural log of 2 over the rate constant. Okay, so that is a very peculiar thing about this first order decay. So, how fast the reaction goes really depends on your starting material, right? How much you start off with. Isn't that correct? Right? Am I right or wrong? Right? So if you have, I don't know, if you're going to make a pizza, how much pizza depends on how much cheese and dough and flour and all that. Here, if it's a first order decay, that reaction doesn't matter how much you start off with. Okay? So for first order, the half-life is independent of your starting material. Right? So that's something some of you may find interesting. And let's do a practice problem here. This one is calculate the half-life of N2O5. Its decomposition has a first order rate constant of 5.4 times 10 to the minus 4 inverse seconds. Okay, so inverse seconds. Our units for lowercase k rate constant are going to be different. All right, so this is just plug and play. And you have the sheet that you can take to the exam. Half-life for first order is natural log of 2 over k. Okay, natural log of 2 on your calculator is 0.693. K here is 5.4 times 10 to the minus 4 inverse seconds. So seconds to the minus 1, I can move it to the numerator. Okay, do you guys know this math? I can move it to the numerator. Seconds to the minus 1 becomes seconds in the numerator. If I move it to the denominator, what will it become? I move it to the denominator, it's going to become seconds to the minus 1. Okay. So again, it's weird, like a first order half-life doesn't depend on how much you start off with. You can start off with a lot, start off with a little. And what will be the units of your half-life? Okay, so I always get weird answers all my 8-9 years here at Methodist. Your half-life is what? Okay, your half-life is a time. Okay, it's a time. So your units are going to be seconds, minutes, hours. Okay, if you're talking about plutonium, your half-life will be centuries. Okay, so if they ask you for a half-life, it's going to be a time. It's not seconds to the minus 1. It's just seconds. Okay, so your half-life will always be a time. So what's 0.693 divided by 5.4 times 10 to the minus 4? On our calculator, what do we get? $12.83, and what will be our units? Seconds, okay? Okay, not inverse seconds. Okay, are you going to write 1283 seconds to the minus 1? Okay, no, that's per second. This is not per second. Half-life is a time. Okay, half-life is a time. Time for what? Okay, half-life is a time where 50% of the material is gone, has decayed. So it is a time where 50% of your material has decayed away. Okay, so for first order, this is the equation I want you to use. Zero order, it's another equation. Second order, it's a totally different equation. So everything depends on decay. All right, let's move on to page 12 here. Okay, with your blessing, I'm going to move on to page 12. All right. So some information about second order, and let's do a second order reaction here. Second order decay. Okay, the reaction 2A goes to B is second order with rate constant of 51 m to the minus 1 minutes to the minus 1 at 24 degrees C. So this is the same thing as 51. We can move that lowercase m down to the denominator. Molar goes down to the denominator. We can move that minutes down to the denominator. Okay, at this temperature. So A naught is that initial or final? Okay. Okay, initial with that little naught symbol, that little O symbol. And then at time t, we go from 0.0092 to 3.7 times 10 to the minus 3. 0.0092 to 0.0037 molar. Okay, so how long this decay occurs? How long? Okay, how long do we go from 0.0092 molar to 0.0037 molar? Okay, what type of decay is this? What type of equations will we use? Yes, Alex, second order. So what equation is that? Okay, don't need to memorize anything. Just bring this to the test. Okay, make sure you choose the right equation now. Okay, 1 over A equals 1 over A naught plus KT. Okay, so I'm going to rewrite this down. Okay, this not always means initial. Okay, always means what you're starting off with. So that's going to be 1 divided by 0.0092 big M. Big M is moles over liter. 1 over A at time t is 1 over 0.0037. Okay, big M, that's moles over liter. Plus K, so K is right here. 51 divided by big M times minutes, both in the denominator, times T. Okay, T here is time. Okay, this is for a second order decay. How this reaction is going to go to A to B. A is going to decay with second order kinetics. So all we got to do is solve for T. Right? So we will take 1 over 0.0037 big M. Okay, I'm going to move this to the other side of the equation. When it does, it becomes minus 1 over 0.0092 big M. This is equal to 51 divided by M times minutes times T. This is what we're trying to solve for, T. All right, 1 over 0.0037 minus 1 over 0.0092. Let's do this together on our calculator. Okay, I think this is right at one. You got it? Is that what you got, Alex? Okay, good. Okay, 161.57. For some reason it looks wrong, but I think it's right. I'll add some extra digits here. All right, let's cross multiply to isolate T. So, oh, by the way, this becomes, I forgot my units here. Okay, the M still goes in the denominator. 1 over 0.0037 M minus 1 over 0.0092 M is 161.575 over M. Okay, this stays in the denominator. Okay, I'm going to cross multiply this out now. So 161.575 big M times minutes. See, I'm cross multiplying, okay? And I'm going to move the 51 down to the denominator. Okay, cross multiply, right? You guys see what I did in this step? The M's cancel, and what's 161.575 divided by 51? 3.17 minutes is the answer I'm getting. So the answer for part A is it takes 3.17 minutes in this reaction to go from 0.0092 to 0.0037. This is second order decay, and we all right, let's do part B for this problem. calculate the half-life for this reaction. And again, we don't need to do anything in terms of memorization. We'll have this sheet for us. Okay, it tells us it's second order. So the half-life is the time it takes for 50% of this thing to be gone. And this is the equation, and this is what we'll use. Okay, second order, half-life. Okay, calculate the half-life for this reaction, second order. All right, so 1 divided by k is 51 m to the minus 1, minute to the minus 1. So minus 1 m and minute to the minus 1, I'm going to move it up to the numerator. Okay, I'm going to move it up to the numerator. If I move it up to the numerator, it becomes m, and minute to the minus 1, if I move it up to the numerator, it becomes m minutes. And the 50 and k, the 51 stays at the denominator. Okay. Right here. So 1 over k, the units go to the numerator, the 51 stays in the denominator. Initial concentration is 0.0092 m. Okay. Okay, minute and minutes cancel, so what's 1 divided by 51 times 0.0092? Okay, 1 divided by parentheses 51 times 0.0092. Okay, don't forget to put it in parentheses. This whole thing is in the denominator. This is just plug and play. Plug and play. 2.13 minutes. All right, so it takes 2.13 minutes for A to decay from initial concentration 0.0092 and after 2.13 minutes, what will the concentration of A be? Half-life. What will it be? 1/2 of that. So what's 0.0092 divided by 2? 0.0046. Okay. That is, in essence, the definition of half-life. Okay. In 2.13 minutes, it will go from 0.0092 to 50% of that, which is 0.0046. Yes, ma'am. Yeah, m to the m to the minus 1, you'll put it in the denominator. Minute to the minus 1, we put it in the denominator. But in this equation, Asia, it's 1 over k. So 1 over this is 1 over 50, just from the equation, 1 over 51 divided by mole over minute. So what's in the denominator of the denominator? What's in the denominator of the denominator goes to the numerator. And then the 51 stays here. Because the equation for half-life, which you just look up, okay, don't memorize it, is 1 over k. Okay, well here is k, so it's 1 over this, 1 over 51 over molar minutes. The molar minutes goes to the numerator. Hey, you see this, Asia? 1 over k, 1 over k, 1 over this. This denominator of a denominator goes to numerator. I don't know if you remember that from long, long time ago. All right, so let's wrap up here on page 13. Okay, here is the equation for a zero order, and the equation is also shown here, and this is just a summary of all the reactions that we have gone through, and this is, will be given on the test. It's all given here. Where's that page? Anyways, it's that page you can bring to the test. Okay? No need to memorize that. All right, we have one final thing here on this chapter, and let's go ahead and do that. Okay, how do you get a reaction to occur? Okay, two things must happen for a reaction to happen. One, they need to collide correctly. Okay, they need to collide with the right 3D orientation. Okay, reactants need correct 3D orientation and speed. Okay, to get to products. Okay, maybe it's like you, Harrison. You play soccer, right? So you need to hit the ball properly, correct? You need to kick the ball in the right speed, and you need to kick the ball in the right orientation. Okay. All right. So same way here. Okay, the molecules must have the right orientation, and they must have the right collision frequency. Okay, so this is an effective collision. Okay, this is not. Okay, this is not either. Okay, and they must have the right speed. Okay, this is not the right speed. So this is not the right speed, and this is not the right orientation. Okay, they need to have the right 3D orientation and speed. They need to have the right geometry. Okay, all of this must happen, okay, in order for a reaction to get to products. Okay. So we need the right orientation and the right geometry. You know how in soccer, right? You have to kick it properly. Okay, don't you need to kick it with the right orientation when you kick the ball? And don't you need to hit it with the correct you need to kick it with the correct orientation, you need to kick it with the correct geometry, right? Yeah. That's kind of the same thing. If you want the reaction to go to products, the molecules must collide correctly. So Harrison, when you kick the ball, don't you have to kick it at a certain way? Yeah. Okay, the reactants have to collide in a certain way. Don't you have to run at a certain speed to get it to where you want it to go? Okay, the reactants have to have the correct speed. Okay, so the orientation and the speed, and then you get to the products. Okay, for that you have to overcome what's called the activation energy. Okay, this is called activation energy, and that's EA. Okay, this is the hump. Okay, when you kick the soccer ball, you have to kick it with the right orientation. You have to kick it with the right speed. Okay, that takes energy. Okay, that takes effort. Okay, for these reactants to get to the right place in 3D orientation, for these reactants to get to the right speed, okay, and to get to the right geometry, okay, they have to summon up some energy, just like when Harrison has to kick the ball at the soccer team, the soccer game. He needs the right speed, and he just can't kick the soccer ball any which way. He has to kick it at the right spot. Okay, that takes some energy. That's his activation energy, to kick the ball so that it goes to where he wants it to go. These reactants have to get some activation energy to get to the right orientation, right spots, and right speed. Then they get to the products. So this is called activation energy. Okay, so if you increase the temperature, okay, more than likely you're going to, the molecules speed up, they get a little faster, and they have different orientations. So usually temperature will increase the speed of the reaction. Okay. Right, so we can have an effective collision, and then you need the right speed. Right, some reactions require energy to go to products. Some reactions release energy. Okay, so this is a reaction coordinate diagram. Okay. So here are our reactants. Okay, A plus B. Okay, this top hump is the activation energy, EA. Okay, it's the energy that the reactants must come to get to the right orientation and the right velocity so that they can collide properly. Okay, we want the right collisions. Okay. Have you ever put a sweater on a small child? How many of you have ever done that? Okay, how is this process to you? Okay, here's this person, okay, baby or a toddler, tedious. And then you have to put the sweater on this child. Okay, as Allison said, it's tedious. Why is it tedious?
They wiggle around.
They wiggle around, wiggle around, wiggle around. So that's a lot of energy on your part, activation energy. Once you get it to, I don't know, their hands get in, and then you put their little head inside the little hole. Okay, once you get everything properly oriented, the head in, the feet, the hands in, the head in, then how does it happen? Then it's smooth sailing down to the child with his sweater on. Okay. But the first part is kind of hard. Okay, they wiggle around, they move around. They jump up and down. Okay, once you get it so that it's just, we also call this the transition state. Right at this point, where all you got to do is stick the head up, pull the arms out. Everything, energetically speaking, is just so smooth. Okay, it's a smooth profile down. So this activation energy is akin to the energy you have to put, okay, or the energy the reactants have to come up with so that they can easily facilitate product formation. It's the hump. Okay, it's the hump. Okay, so if you see this, okay, just realize the activation energy is the peak. Okay, once you get to the peak where Allison and anyone else who puts a sweater on a toddler, on a small child, once they put all this effort and energy right to this point, at this peak, it's called the transition state. Like I said, okay, putting on the sweater becomes easy, but the first part becomes hard, okay, because they move around a lot and they don't want to put on the sweater. Okay, some cases, some reactions, after you put on the sweater or after the reaction is all said and done, they actually release heat. Okay, they release energy. So we call that an exothermic reaction. Okay, so you put on, I don't know the example here, but once you put on the sweater, they just they blow up. Okay, they release a lot of energy. Okay, sometimes, this is probably the case here, this would be endothermic, putting on a sweater on a child. Sometimes, for reactants to go to products, this requires energy. How notice one releases energy, and an endothermic reaction requires energy. Okay, so some reactions release energy as they overcome their transition or their activation energy and reach their transition state. As they go down to products, they release energy, and some require energy to reach their transition state. Okay, so they require energy, and the products that are more energy than the reactants, so you need to put in this much energy gap. Okay. Okay, those reactions that require energy is an endothermic reaction. Those reactions that release energy is an exothermic reaction. Okay, the energy hump is called the activation energy. Right at the peak is called the transition state. Okay, transition state. Alright, so this EA is something new to us. It's an activation energy. Okay, the right collisions at the right 3D orientation. All molecules are 3D. All molecules are 3D. Okay, if you like 3D, chemistry is the subject for you. All molecules have a 3D orientation and a 3D geometry. Okay, to get to that state where they can easily go down and make products, okay, that's called the activation energy. Okay, EA. All right. And some reactions just release energy. Some reactions require energy to, get to product formation. All right, now let's go over our last equation here. I'll give you this equation on the exam. And this last equation is called the Arrhenius equation. Okay, so rate constant on the y-axis, temperature on the x-axis, and this is what it looks like, okay? It looks just like vapor pressure on the y-axis, temperature on the x-axis that we saw before. Right? And the equation is exactly the same as before. All right? So I'll give you this equation. Let's move on to page 16 here. This is the Arrhenius equation. Okay? Can you remember this equation from our last exam? Okay. Yes? Okay, this is our equation from last exam. The Arrhenius equation that I'm going to teach you is just like this. Okay, remember, this looks like vapor pressure versus temperature. Rate constant versus temperature. It looks like vapor pressure versus temperature. So instead of P1, we'll have rate constant K1 divided by rate constant K2. Here, the hump is the activation energy, whereas here in last test, the hump for the vapor pressure was delta H vaporization. R is R, and then 1 over T2 minus 1 over T1. Okay. So this is called the Arrhenius equation. Right, the idea is this. You have a rate constant K1 at some temperature T1. If you raise the temperature or lower the temperature to, say, T2, what happens to your rate constant? Okay, it will change, okay, because this is quoted at a specific temperature. So you change the temperature, you change the rate constant. So this rate constant, lowercase k, is quoted at a specific temp. Change rate constant for a reaction. You change, you change the temperature of a reaction, you change the rate constant k. Okay, what I'm trying to get to you guys, is that this is what we had in our last exam, and this is the exact same homology. It's exactly analogous. Okay, everything is the same, because these are kind of look the same, and they're both quoted at a specific temperature. You change the temperature, you change the rate constant, you change the temperature, you change vapor pressure. All right? So I'll give you this on the exam, and let's do a practice problem. You'll see something like this on the test, so let's go ahead and do this. right, the first order rate constant for the reaction of methyl chloride with water to produce methanol and hydrochloric acid is 3.32 times 10 to the minus 10 inverse seconds. Okay, seconds to the minus 1 is inverse seconds. And this happens at 25 degrees. So this is K1 at 25 degrees, T1. Calculate the rate constant at 40 degrees. Okay, T2, the activation energy is 116 kilojoules per mole. Right, so we're going to use the Arrhenius equation here. Okay, which is, I'll give you this on the exam. We have rate constant K1 at 25 degrees divided by rate constant K2, okay, is equal to the activation energy divided by R, 1 over T2 minus 1 over T1. All right. I'll also give you not only this equation, I'll give you R. So R is, I'll give you it. You don't memorize it, and you don't memorize this equation. 8.314 joules over mole Kelvin. Okay, this is R. All right, so the first thing we want to do is we want to convert our temperatures to Kelvin. Okay, why do we want to convert our temperatures to Kelvin? Because the R constant has units of Kelvin. Okay, so we're going to convert our temperatures to Kelvin. Okay, so 25 degrees C, what is that in Kelvin? We add 273, which is 298 Kelvin. We'll just do, 298 Kelvin is good. Okay, so that's K1 at T1. Let's do K2 at T2, 40 degrees C. What's that? Plus 273. 313? All right, this next thing we'll do is we will convert the activation energy to joules over mole. EA, which stands for activation energy, that's the hump. The energetic hump will convert to joules per mole. The way you want to do that is multiply this by 1,000. Why did we convert this to joules over mole? Okay. Why? Because of the units of the constant. Very good. All right, now we will plug it in. I'll write plug and play. Or should I just write plug it in? Plug and play into equation. All right, so natural log of K1. K1 is 3.32 times 10 to the minus 10. We'll put that in this ink. Okay, no units inside the natural log. Okay. K2, what's K2? That's what we want to solve for. Equals EA. What's EA? 116,000 joules over mole. Joules over mole. Okay, what's R? 8.314 joules over mole times Kelvin. Okay, the units will cancel out, so it should be okay. And then what's 1 over T2? 313 Kelvin minus T1 minus 1 over 298 Kelvin. All right, how do we do this on our calculator? Okay, you guys want to do this on our calculator together? Okay, let's do this together. Okay, first I would do this thing. Okay, this messy fraction. 1 divided by 313 minus parentheses. Put those parentheses. Minus 1 divided by 298. Close those parentheses. I get that weird, messy number. I'm going to take that and I'm going to multiply it by 116,000. You guys with me? I got that. Everyone with me? Okay, I just need one person to be with me and then I'm good. Divide that by, so this times this divided by 8.314. Okay, this is what I want to write. Minus 2.243. I'll add some extra digits here. 77. Natural log of 3.32 times 10 to the minus 10 divided by K2. All right, how will we solve and isolate K2? Okay, so we will take the inverse natural log of both sides. Okay. Take inverse natural log of both sides of the equation. The inverse natural log is called E. Okay, remember this E. So E to the power of natural log of 3.32 times 10 to the minus 10 divided by K2 equals E to the power of minus 2.24377. E to the power of natural log of this number is this number. Yes? E to the power of natural log of anything is anything. Okay? They are, I don't know, what do you call it? Yin and yang. Okay? Opposites attract. Inverses. E to the power of this number, let's calculate that on our calculator. Okay, so on our calculator, we're going to do shift natural log, or second natural log, whatever it may be. Shift natural log, shift, and then the natural log button. Negative 2.24377, negative 2.24377. Okay, close those parentheses. 0.10606. 0.10606. All right, we'll cross multiply to isolate K2. Okay. Okay, cross multiply. So K2 is 3.32 times 10 to the minus 10 divided by 0.10606. And what did you guys get when you do that? .32 times 10 to the minus 10 divided by 0.10606. 3.13 times 10 to the minus back in. Units are inverse seconds. Okay, and this is our answer. So K1 is 3.32 times 10 to the minus 1 per second at 25 degrees C. Okay, you raise the temperature to 40 degrees, and the rate constant is 10 times faster. 10 times faster. This reaction is 10 times faster. To the minus 10 to 10 to the minus 9. So something like this on the exam. Okay, so yeah, so make sure you brush up on this. We'll have a review and go over another one for our test review. Okay. So the activation energy and K1. Okay, you change K1, you change the temperature, you change K, rate constant K. All right, so something like this on the exam. Check your homework, check your quiz, and we'll go over this one more time during the review. All right, the last page of chapter 13 has to do with a catalyst. Okay? So the only thing I want you to know about a catalyst is that it will lower EA, this activation energy, this hump. Okay, so this is uncatalyzed. Okay, and look what happens after you catalyze this reaction. Okay? The EA will go down, hence the reaction goes faster. Okay, if the reaction goes faster, that means your rate constant increases. Okay, because if your rate constant increases, that means the reaction goes faster. So your rate constant increases. So let me give you an example of this. Okay, before I let you go, give me 2 minutes. I can tell you an interesting story. You ever buy potatoes from the grocery store? Potatoes? I guess this is a potato. All right, if you take a potato and cut it up, and if you take this potato and put some hydrogen peroxide, which you can get from Walmart or CVS Pharmacy, what happens is that you'll get water and O2 gas. Water and O2 gas. Okay. So what happens is that this H2O2 is going to react with the potato to give you H2O plus O2 gas. The gas will be oxygen bubbles. Okay, this H2O2, which is called hydrogen peroxide, that decays to water and oxygen. This happens in the time span of years. Okay, that's why when you buy hydrogen peroxide from Walmart or CVS, it's hydrogen peroxide. It's not water and oxygen gas. Okay, but if you put potato, which is a catalyst, this happens within a span of minutes. Minutes from years to minutes. Why? Because potato has a catalyst. Okay, this catalyst is called catalase. Okay, it's an enzyme, and you may know from biology class that enzymes are catalysts. Okay, they make the reaction go super fast. And this potato, the potato cells are heavily enriched in this enzyme called catalase, okay, which converts H2O2 to water and oxygen gas. You can measure the oxygen gas because it will displace the water. Right, so this is an example of a catalyst. And nobody knows how it works, but in this case, the potato has this enzyme. Other catalysts like there's an anti-cancer drug called cisplatin. It's used to treat certain cancers, cisplatin. And nobody knows how it works, but somehow it increases the death of the cancer cells more so than others. There's many examples of catalysts, and that's for your higher level classes. In this class, just know it will lower EA and increase the rate constant. Okay? And have a good weekend.